Hi everyone, take a look at your enthalpy of dilution in water lab. Now the good news is we kind of already talked about this when we talked about solutions, and if you remember I showed you a enthalpy diagram. I'll hopefully flash the same one up that I have in that solutions packet, but it looked kind of similar to this, right? Okay, so let's just remind ourselves of the basics, because honestly I don't like how it's discussed in the pre-lab for the experiment. All right, so these couple of pages here tell you the same thing, but honestly I don't like how it's explained. Right, so let's just talk about how a crystal like sodium chloride, for example, any ionic material would dissolve. Right, okay, so the first thing we have is, well, let's just step back from this even. Let's just remind ourselves about a simple Hess's law situation, right? So remember, we have enthalpy, right? So inside every reactant and inside every product there are chemical bonds, ionic, covalent, whatever they are, right? And if you like to think about it, I like to teach you like this. Those chemical bonds are like sticks, right? So there's a stick holding one atom to another. And that stick can be snapped. That's breaking a bond, which costs energy, right? So what happens in a reaction is you break all the bonds in the reactants. They form essentially atoms. And then they form bonds with new atoms, which we call products. And it costs a certain amount of energy to break the bonds. And you get more back, usually exothermic, when you make the bonds. All right, so that's why exothermic reactions are so popular, because the products have stronger bonds than the reactants. Okay, so therefore that's where we get a negative delta H, right? Okay, so let's talk about that. So if I have reactants here, okay, now I break all those bonds that cost energy, yeah, and then I reform them to make products. Reverse process, okay, gives me energy back, yeah, okay. And we like to say delta H is negative. There's a loss of stored energy, right? Okay, and that comes out as heat. So it's a weird sign convention, all right? We won't talk about the sign convention, but just know, first law of thermodynamics for an exothermic process, minus delta H equals plus Q. The energy difference between the bonds in the reactants and products comes out as heat. Okay, fair enough, right? Now, when we have a dissolution, that's a special kind of reaction, okay? So let's think about it. So always have this kind of in the back of your head, yeah? And this is the first law of thermodynamics right here, okay? This is the primary law we're going to use, right? And then Q equals CPm delta T, which you may remember from 100 calorimetry. We'll get to it. All right. Now, so here's your enthalpy diagram for dissolving, right? So you start with a solute and a solvent. Solvent's water, and it may be NaCl, some ionic solid, right? Now what you got to do, you got to break the bonds in the reactants and then form bonds in products, right? Fair enough. So where it says Le, you may remember that from the solutions packet. That should actually be a plus there, right? Okay, you're going to actually put energy into a crystal to break all the bonds. That's called lattice energy. So Le is lattice energy. It's not like one Na bond to one Cl. It's like, because it's a radiative ionic bond, every ion's bond to every other oppositely charged ion in a crystal, right? Because it's, you know, distance of attraction for charges thing, right? So it's not right to say bond enthalpy, it's lattice energy. Anyway, same kind of thing though, right? So it costs X amount of kilojoules to separate all the ions in NaCl out into gaseous ions, say. Right? So it's just theoretical. It's not something you would do in an experiment. It's just how the math works, right? So that's the lattice energy. You have to separate out the ions, okay? Technically, you also have to separate out the water, but that's such a small amount, it doesn't matter, right? Because there's gaps between water molecules. All right, now over here, this is where we actually add the water to the ions. And if you think about it, if I have a plus ion, then the water has an O, H like that. We saw this little kind of tractor trailer deal, right? Water is polar, has a plus end and a minus end. And as we talked about in that solutions packet, why do things dissolve? Because there's loads and loads and loads of weaker ion dipole bonds which overpower the limited number of ion-ion bonds, right? And that's why this gap here is bigger. So if you look at it, you get more energy back by forming like shells of solvation, right? So all those little bonds add up to a stronger force by this much. and that's heated solution, okay? So the difference, the difference between the lattice energy and the hydration is what's called the solution energy, right? Now, if it's like the previous example, if it goes down further, that's an exothermic, right? So if it, this is like our original chart, right? So if it's below where it started, it's exothermic. Delta H will be minus, heat will come out, right? If it's below, yeah. So sometimes you dissolve something in water and it seems to heat up. That's because this is lower. Fair enough, right? Now, how do you measure that? Well, that's back to your calorimetry. Now, I don't like when the book does this, they use S, right? The actual formula is Q equals Cp m delta T. You may remember that from calorimetry, hopefully in Chemistry 101. So the heat capacity of water, 4.184 joules per gram degree C. Mass of the solution, temperature change, right? So obviously the temperature of the solution heats up when you dissolve something, that's in degrees C, right? Okay, and then you can work out Q and delta H, all right? So you can, this is numerically the same value, but remember, this is going to give you an answer in joules. You may probably have to convert to kilojoules for delta H, so just, divide by 1,000. All right, so that in essence is dissolving ions to find delta H. So you measure the temperature change, throw it into the calorimetry experiment. It's mostly water, so use the heat capacity of water, the mass of water, and the heat change of the water or the solution, right? The same kind of numbers. And then, hey, Q equals delta H. You can find delta H. If heat comes out, delta H is minus. Good to go. All right. Remember, that's usually in kilojoules, so divide by 1,000 if this comes out in joules. Fair enough. Now, here's the interesting thing. You may get a solution, and I'll kind of annotate my diagram, where it doesn't quite get to the bottom, and that was the one from the notes, right? So say it only stops there. That would be an endothermic reaction because delta H is positive in that case, right? Okay, so if it stops short of the, the break-even line, so to speak, it's going to be an endothermic. Oh, excuse me, I'll just tell my telemarketer to go away. All right, now, so if we stop short of the break-even line, so to speak, that's an endothermic process. So you put your hand in, when you try and dissolve something, it might feel colder, right, because it's endothermic, yeah. Now, remember, we now have Gibbs free energy, right? So I did say back in the solutions packet, hey, you can make things dissolve by stirring them. Why is that? It's kind of neat, right? Because delta G equals delta H minus T delta S. And we talked about the magnitude of delta H and T delta S in the note packet, right? So if you want delta G to be minus, which would be a truly spontaneous process, so you always want that to be minus, right? And most of the time it is, because delta H is always a really big number in kilojoules, right? So if you've got an exothermic reaction, this is sometimes irrelevant because this is in kilojoules, this is in joules, right? Okay, so that's why 99% of the reactions that are exothermic are spontaneous. You set fire to something, it sets on fire, right? And then, if you think about it, well, if it's a positive delta H, it's probably not going to be spontaneous, but certain reactions that are endothermic are spontaneous because you can make them happen by playing with this number. So you can heat them up, make the T factor bigger. So if the magnitude of this exceeds the magnitude of this, and this is negative, delta S is positive, minus T delta S is negative, like we saw in the notes, it will win, right? So if you think about it, when you stir stuff to make it dissolve, what's happening? You're actually increasing delta S. You're increasing the randomness of the system. Okay, if you also heat it up, it's the lab trick, right? How do I make my stuff dissolve? Well, you kind of stir it on a hot plate, right? So when you stir stuff on a hot plate, you're increasing this one, you're increasing this one. It's going to turn into a spontaneous process, even if it's slightly endothermic. Interesting. So you can dissolve things by playing tricks with temperature and enthalpy, randomness. Okay, and that's kind of where it goes in the second part of the lab. You can read about that. But I just wanted to kind of bring you up to date with the basic principles. If you need to go back and look at the Chemistry 101 stuff, I do have a link to that for Hess's law. Make sure you're thoroughly familiar with the delta G stuff and also the calorimetry stuff, maybe from 101. It's kind of straightforward and you've done it before many times, but look at it if you need to. Okay, I'll put links to that on on the assignment, right? So I just wanted to get over this kind of weird stuff they talk about here and talk about it more in a kind of a true kind of chemistry way. Okay, this is all accessible through Pivot, so it's all done through Pivot, and you can just submit it there. Deadline always is Friday. Okay, so back to normal deadlines now. I know we had a couple of labs last week because we had to get a couple of we did an extra lecture and we saved the lab until the next week. So we're kind of caught up now. You're actually slightly ahead. Okay, so we're actually slightly ahead of where we need to be in lecture, which is right where I want it. I want us to be slightly ahead of the labs in lecture, so we're prepared before we do the lab. So you should be in good shape. Just do that thermochemistry packet. Look at the old stuff if you need to from 101. There is a link, and you can look me up on YouTube. Right? Okay, don't look up Rate My Professor. We can spend time talking about that, but yeah. So anyway, any questions, discussion, or we'll call the chat. Okay, see you guys next time.